As Jakob said, this is a collaboration between, well, I started with DIKU Alumni, and now that I'm in Oslo, we also included that as well. So I actually can do research together in a wider sense. So this started looking at and coming back from some of Maja's earlier work on measuring energy consumption and understanding energy consumption. And falling into what Jakob said, it sort of interests me because it comes down to some of the fundamental understanding of computations and what we do. So why should we do this? Well, if we look at what sort of we expect, then about 2% of the CO2 is said to be from aviation. But actually, even more of it, it's an estimate between 2 and 3% is actually used by ICT today. And this is even a bit older number, some of this. Today, with machine learning, AI, and what we're pushing into that, then this is expected to rise extremely fast right now. Really exponential growth over the next coming years. So it is a problem that we should consider when we're talking about energy and climate change. But what we usually think when we are using and talking about think of energy is that, well, we just have the computational part of the that we use the electricity, but actually a big part of it goes into production of the machines. So every time you throw out a machine, well, you have actually thrown away a lot of the energy that you use. So recycling is also a part that we need to focus on. But we mainly focus on the energy consumption because that's what we can actually do something about. So how does this work? Well, energy consumption in ICT is a lot of things. A lot of it is used by the devices that we have, the TV, cell phones and computers and everything. The network is actually also consuming about 20% of the energy consumption that we have today. I heard some numbers that this is actually quite bad the way we're using it, because less than 20% of the capacity of our data nets is actually used, but they still take up 20% of all the energy consumption we have. And we are still throwing more into it because, well, we want more network. And if we're looking at data centers, then this is, well, with these numbers we have from 20, it's 22%, but that's expected to increase extremely fast now with the training of AI and similar things. And yes, as I said, this is actually the old numbers from 2020, with the expectation of it growing to, I don't know, with 50%. But right now, this will be extremely much more than what we expected it to be. So what should we do as computer scientists? Numbers show that actually only 82% of, as much as 82% of developers do not consider energy consumption at all. We even have a problem getting students to optimize the code for runtime. So now they have to consider another factor into it as well that is even harder to understand and harder to measurement than just doing some tests on their computer. And only 10% actually have tried to do something measurements with energy consumption. So there's a huge potential in actually getting people to use some of the things that we're trying to understand in research. But the problem is also that it is quite hard. And there is a lot of problems that we need to address. So here's a few use cases. I will let it take over to Maja.
Thank you. So doing something about the knowledge of how we consume our energy when we execute our software. So one of the things we looked at was a simple question, time complexity as we know it. How does that relate to energy consumption? Is it related at all? And 2 months of data collection. This is a bubble sort. You have the exponential worst case. And actually, what we see here, the brown dots or the brown triangles are the random. We have the worst case is the purple. So we have the input sizes in the bottom. And the further you go right, the larger the input sizes. It should be, as we have been taught in algorithms, that the worst case is actually the worst case. But if you run energy consumption measurements, you will see that the random input, and not the worst case, which is typically the reverse order, is the one that uses the most energy. The good question is then, why? So the branch predictor is optimizing things that are doing the same things every time, so the same execution paths. If you have a reverse sorted, you will always run into, is this number larger than the other? Yes, and then go with that one. So it's actually the branch prediction that helps the worst case here. So the worst case is not the worst case. And this is just how we compared them, because there is currently no way of comparing So, sorry, how do I explain that one? So, we wanted to say something about it, it's n squared, right? But how do we say that that the development is n squared? What we did was, instead of trying to compare that line, fit that line, what we did was changing the input sizes. We squared the input sizes instead. And that gives us straight lines. And straight lines we can very easily see whether they are straight or not. So that's the way to compare and see whether they are n squared. So this one shows that the energy and the input sizes are totally related. Actually, 99% of the variance that we see can be assigned to this part. So going from the top, in the very top of our tech stack, we have the algorithms. The next part is our software. So how do we implement stuff? So when we do programming, a lot of us do modularized programming. So we can change module with newer, more efficient modules if whatever, we have a good idea or something. So can we actually show whether changing modules will change the energy consumption? And can we measure it? And the answer is yes. So what we did here was we took a look at the WordPress plugins, which are very finely modularized plugins. So they provide us with new functionality. So here in the top, we can see that we have a WordPress site with no plugins. And then we have a specific user flow going through that website, measuring the energy. So this is what is the energy consumption of a typical user flow. Then we turned on something called Elementor. Elementor is a pretty fine plugin that takes your very old style 90s web page and make it very modern and lovely to look at. But it also costs a lot of energy. So we can see here that if we have no plugins, it will use a little more than 100 joules for each user. If we turn on this very lovely styling thing, it uses a bit more in the median. The typical user flow will use a bit more than 300 joules. What do we get? We get pretty. We have the same text, the same information, we just get pretty. So now we can actually figure out whether we want pretty with the cost of the energy, or perhaps we can get pretty in another way, which is less energy costly. Then we have two plugins, one called Imagify and one called EU. And they are image compressors. So on the website there are images. As soon as you download an image, the amount of data that you transport over the internet will say something about your energy consumption. The larger the amount, the more energy is consumed. So when you compress the images, you use less energy. Nice. And here we see a very nice indication that using one algorithm or another algorithm for compressing the data actually matters. So our choices as computer scientists or as software developers, our choices, they matter. Not just the choice of functionality, oh, should it be pretty or not, but actually what we're doing. And that's interesting. So this is the server side, how this web server is serving the pages. If we take a look at, yes. On the client side, you will have a similar picture. The exact same. The last case that we brought with us is looking into Haskell. Haskell is fun and functional programming is lovely. So what we did was we looked into the Haskell compiler and the different flags of the different parts of the O2 flag. So, nice, this is our experiment. So we have a series of benchmarks in the bottom. Then we have a series of flags, all the flags that you can. So when you have your O2 flag, it actually consists of a lot of different transformations. Some of these transformations are created such that one will prepare the code for the next one. So what we did was we took all the flags and then we turned off one flag at a time. So that's why they have typically are called if no and then the flag for the transformation that it indicates. So here we can see pairwise, if we turn off one flag, will it help? So will it increase the energy? So if we turn it back on again, will that help? So all the green dots here, they help. All the blue ones have the exact same, or not exact, but we cannot show significance. They will not do anything to our energy consumption. The red ones are the bad ones, right? The red ones will increase when you turn the flag on, when you turn the transition on, they will increase the energy. You have a question?
Yes. What's the difference between the process and the circles? What do they signify in the plot?
That's a good question. So it depends on which statistical test we use to prove this. Yeah.
Is there a reason that you only use the process on a relatively fewer amount of tests?
Yes, absolutely. Because when we do statistical tests, statistics, what we do is we typically assume that our data is normal distributed, which holds sometimes. And we want to do this because they are typically the most powerful ones that you can apply. Those are the round circles, the ones that are the most of. If we do not have a normal distribution, for instance, sometimes our computers turn on services. Turn them off, on, off. So we will have a measurement curve going, and typically it will not have this very nice bell shape, but a bimodal one. That they are not normal distributed, so we cannot use normal distribution tests. So we do something else. Good question. Then we took a look at time here. So these are same pairs. We just looked at time, and there was a bit of a surprise, right? Because only 26% of all these pairs actually was improved by the flag. 20% we had the time was increased. The execution time, adding that flag, increased the execution time. That is kind of weird. And then we have, again, the squares and the round ones. This is where the time and energy are reversed. One is better, the other is worse. So, for today, we have shown that we actually can now measure the energy consumption of programs, which is nice because now we can start talking about it and use it in our development. And we have also showed that optimizing the code somewhere in the tech stack, starting with the algorithms or the compiler level, whatever you like, your preferences, it actually improves energy consumption, or it can improve energy consumption. And the last thing I like to think about is that with so many users, we use IT every day. From the morning when the clock is ringing, that's our phone, that's IT. We have a huge potential to improve the energy consumption of IT. Thank you.